right, ladies and gentlemen, we'll go ahead and get started for today. Today we're going to be continue our discussion about the interior of the Earth, and we're going to be working on what's the day? Here we go, day 15. Okay, so if you go to day 15, we have the assignments that I gave you guys yesterday on paper here as backup. We have notes, fill in the blank notes. This is the article we're going to start with today, the Alfred Wegener article, and then the practice as well. So do me a favor, go ahead and open up the Alfred Wegener article. So what we're going to do first today is we're going to read about a gentleman who was one of the first people to start thinking about the Earth and question whether or not the map has always looked the same since the beginning of time. And he's going to propose a theory of plate tectonics and continental drift. As you read through this, I want you to focus on his four main pieces of evidence that he had to support his theory of continental drift. And that's echoed here in the two questions. There's only two questions on this article. So the four main pieces of evidence is the key that you need to get out of this article. What four things did he say to support his theory of continental drift? And then the second part is, why was his theory not accepted? While he got a lot right, he did get some things wrong. He made some bad hypotheses about how it was working. And I want you guys to figure out, what did he get wrong and why did people not believe him at the time? We're going to find out that he was in some terms correct in terms of his theory, but again, he couldn't really support it with the driving mechanism. So that's what I need you guys to find out. The four pieces of evidence that he did to support, and then the one thing that he could not put together to help his theory. So I want you guys to go ahead and pause the video right here because I want you to read this first. I'm not going to be going over the answers because I think it's very easy to go through this and get that information. So once you have those two questions answered, then please unpause the video and we will continue on with the notes. So please pause at this time and read the article and answer the first two questions. Okay, I'm going to assume at this point, if you're continuing to watch the video, that you've already read the article and you're familiar with Alfred Wegener and his work. So I'm going to be discussing this as if you've already read the article. Again, please, if you've not read the article, pause the video, go back and read the article first, okay, and then unpause it and we'll continue on with notes. So here we go with the notes. All right, so continental drift and plate tectonics. First off, we know that evidence for continental drift first came from Alfred Wegener. He was working in the late 1800s, early 1900s, and his theory was that he believed all the continents were at one point connected in a single landmass called Pangea. Okay, so he named that Pangea, which means all Earth, and that was he said that last broke up about 200 million years ago. Now, he had a couple of different pieces of evidence to support his theory. The first is the shape of the continents. He was looking at the coastlines of South America and Africa and noticed that those two look very similar, almost as they were puzzle pieces that could go back together. And so what he started to do was kind of work back in time to see how do the continents fit together? Is there a way to kind of put them together almost like a puzzle? And this was just one of his pieces of evidence. He again named that all Earth Pangea. It's right up here in the upper right corner, or excuse me, upper left corner right here, Pangea, with all the continents forming one super landmass. And then he said that they split up and that they have been drifting to their current positions ever since. That is the theory of continental drift. They were all one point together, but then they broke up and they've moved to their current locations. So that was just one piece of evidence, the fit of South America and Africa. Now, that wasn't the only thing that he had. He also supported his theory with the evidence of fossils. Fossils of the same prehistoric organisms, whether it be plants or dinosaurs or whatever, were being found separated by giant oceans. So if you look here on this map, this is showing you that there is a dinosaur that was found both in southern South America and southern Africa as well. Now, there's a giant ocean in between. So the question is, well, how did they get there? Well, remember, the current thinking was that there were land bridges and that these animals migrated from continent to continent. That's incredibly far, not very plausible for a number of reasons. again, Wegener was looking at the continents, and when he put these two back together, again, you can see how this kind of fits right in here. When you put these back together, all of a sudden these bands of fossils are not separated by great oceans. They're all existing in one spot. And then the idea is that the continents split and took the fossils with them. This happens with a lot of different fossils, whether it be from South America and Africa or India, Antarctica, and Australia. So he continued to look for these patterns and continue to find evidence that, hey, these fossils are showing up in all these different continents separated by giant oceans. Well, that's not really plausible. So what's the best explanation for that? Well, they were at one point all together, and that's just where the dinosaurs existed. The fossils have been moved with the continents ever since. Not only that, but he did also find that mountain ranges started to match up. So the Appalachian Mountains in North America, some of the mountains in Northern Africa is also same age, same formation, also with the Scottish Highlands as well. These are all the same age, same formation, so they were created at the same time. The idea is, how is that possible? How are all these mountain ranges the same age, formed the same way, from the same pressure, if they at one point weren't together? Also, South America and Africa again, also had some mountain range systems that lined up. Then he also found warm climate fossils in Antarctica. So the question is, how did tropical plants get in Antarctica? Was the world at one point in time so hot that Antarctica, the freezing ice cube of a continent, was that at one point a tropical paradise? Well, probably not. So that led him to believe that, you know what, these Antarctica maybe wasn't always in its position that it is right now. So maybe at one point in time, Antarctica was closer to the equator, and hence the tropical plants. He also found evidence of glaciers in areas that are now tropical. So again, what happened? Was the Earth so cold at one point that the tropical rainforests were covered in glaciers? I don't think so. So the question is, how did that get there? Well, they probably weren't always at the latitude or longitude that they were today. So how could the continents be drifting? On top of all that rock, fossil, and climate clues that were evidence to support his theory, he was rejected because he couldn't explain how the continents move. Remember, he thought that waves and tides were moving the continents, but that's not really possible because those waves and tides would literally, shred the Earth. It would cause all kinds of terrible problems, and it would require such an incredible force that it would probably stop the Earth from spinning, which would cause a lot more problems as well. So while he got a lot right, and we also can measure it today using satellite technology and stuff like that, we do know that he was correct in the fact that the continents are in motion. But the problem is that he could not explain how. He did not know what was going on inside the Earth to drive that plate motion. So this brings us to our modern theory today. We call not continental drift, but plate tectonics. Okay, plate tectonics is the idea that the Earth's crust and upper mantle are broken into sections called plates or tectonic plates that move around on top of the mantle. So remember, the composition of the Earth's plates is the lithosphere. That's the solid part of the crust and the upper part of the mantle. So this is the solid portion, and they are floating on top of the asthenosphere, that plastic-like layer that's right below it. So this is what's going on. And because the plates are moving, they can form one of three different types of boundaries. There are divergent boundaries, convergent boundaries, and transform boundaries. We're going to go through each one. Let's first talk about divergent boundaries. Divergent boundaries are boundaries where two plates are moving away from each other. Plates are being pulled in opposite directions. So you can see plate A over here is going to this side, plate B over here is being pulled to the right, and that's going to lead to a very slow erupting volcano in the middle. What's going to happen is as these plates move away, the pressure decreases. We talked about this yesterday with our discussion on the Earth's layers. When you release pressure from the asthenosphere, that plastic, slow flowing solid that liquefies because there's less pressure, it fills the gap, it hardens, and it creates new sea or new crust. So in this case, it's new oceanic crust because this is showing us something that's underwater. So this happens a lot on the map. If we were in the room, I would show you, and I'll point it out tomorrow, but I would show you the map with all the ocean water removed so you can see the ocean floor. And what you would see is these giant cracks that go all around the Earth's crust on the ocean floor. And there's actually one of these divergent boundaries in the middle of the Atlantic Ocean on what we call the mid-ocean ridge or mid-Atlantic ridge. And what's happening there is the plates are moving in opposite directions and there's new seafloor created. So that means closer to the crack is newer crust, and as you go further away from it, there is older crust. This also means that the United States is getting further away from Europe and Africa because these plates are growing. The Atlantic Ocean is getting bigger, okay? So divergent boundary, plates moving apart. Convergent boundaries are where two plates move together, okay? We have to remember that there are two different types of crust. There's continental crust that is thicker and less dense, and there's oceanic crust that's thinner but more dense. So because of this, there's three different types of convergent boundaries that can occur. The first is when an ocean plate collides with a continental plate. When an oceanic plate collides with a continental plate, the oceanic plate is more dense, it gets pushed down into the mantle and destroyed. Then the continental plate gets pushed up and just kind of rides along the top of that. I'm going to show you a picture in the next slide that'll make that much more clear. You can also have an oceanic plate colliding with another oceanic plate. That's going to create a very deep sea trench because where the two are meeting, there's going to be some downward bending, but one is going to be subducted or pushed down into the mantle and destroyed, and the other is going to kind of ride along top, and it can kind of create volcanic islands. I should have said that first one where this oceanic plate being pushed under a continental plate will create volcanic mountain ranges. We'll talk about that in a moment when I show you guys the picture. The last possibility is if you have a continental plate and a continental plate. Neither one of these are going to be really pushed down that much, but it's going to create giant mountain ranges because a lot of it's going to get pushed up because both of these have a very low density, and so they're going to kind of resist sinking beneath one. They're going to push upward. So there is a continental collision still occurring to this day, and that is between India and China. If you know what's there, it is a mountain range visible from space called the Himalayan Mountains. So the Himalayan mountains are actually still getting bigger because this collision is still occurring. So we take a look here. This is the first one, oceanic and continental. Oceanic plate is being what we call subducted or pushed down into the mantle. And that friction that happens there where the two plates are rubbing together liquefies a lot of that rock. And that's why you get volcanic mountain ranges. The oceanic and oceanic, again, one is going to subduct under the other. One's going to be pushed down and destroyed. That's going to create a little deep spot in the ocean. We call that a trench, and this can also create volcanic islands. So a lot of places around the Pacific Ocean, you'll see these, and we'll talk about that more tomorrow in class when I can show you the map. Then we have the continental crust. So this is like the Himalayan mountains. One will somewhat be subducted, but there's going to be a lot of upward pushing because these are both very thick, very low or lower density compared to the oceanic crust. And so they're going to create large mountain ranges. Now, if you're not moving apart, you're not moving towards each other, what's the other option for motion? Well, where you slide past one another. And this is called a transform boundary or transform fault. You'll hear me say both interchangeably. So again, these are two that are moving horizontally. You can see in this picture, one is moving kind of the southeast and one is moving northwest, and that causes deflections. You can see that in rivers and streams a lot. If a river crosses one of these boundaries, a lot of times it will just kind of dogleg like that. It'll kind of be going one way, push up, and then go the other way. It wasn't that this is naturally occurring. That river was at one point in time straight, but because the plates have moved in opposite directions, they kind of stretched that river out. So it's no longer one straight line. There is a giant transform fault in the United States. You can think about somewhere where there's lots of earthquakes like California. I don't know if anyone has ever heard of the San Andreas Fault, but the San Andreas Fault is a transform fault. Not all of California is part of the United States. It's not part of the North American plate. Some of it's on the Pacific plate. So what that means is that part of California is actually shifting. It's deflecting southward and the North American plate is deflecting northward. And so eventually somewhere like Los Angeles in a couple 100,000 years could be even more of a suburb of Mexico than part of the United States. So obviously these collisions are going to create different landforms. Landforms that can be things like rift valleys. So that's what happens when there's two continental crusts being pulled apart. It's just kind of a very flat valley. There's mountain ranges, continental collisions, volcanoes. Again, that's going to be another convergent one, and false. That's on the transform boundaries. Now, what could Wegener not explain? What did he not know? What is actually driving this plate motion? And it's something called convection currents. We saw this with the air when we were talking about how heat moves through the atmosphere. Remember, hot air rises and then it gets higher in the troposphere, it cools, so it becomes more dense, it sinks, and then it hits the ground where it's heated, becomes less dense, and rises. That whole process that has happening in the air is also happening inside the Earth. We know as you move down, temperature goes up. So as you get closer to the core, the temperature increases. So what happens is the rock sinks down towards the core, it gets heated, or lower in the mesosphere, lower in the mantle. It gets heated. That causes that rock to become slightly less dense. That rock rises, then it hits the crust where it is cooled. It pushes outward, right? It's cooled, it becomes more dense, and it sinks. And you get this kind of repeating process. I'll do my best to kind of make a little drawing, but it's not going to be very good. Let's do a little quarter Earth. Oh, wow. Let's start that over. That's terrible. That's just bad. All right. So actually, let me just do it down here at the bottom and just do like a little half moon. That's a little bit better. Okay. So if we have the core right here, again, the core is hot. That rock is going to rise, and then it's going to be deflected outward. And as it is deflected outward, this would be a divergent boundary. Okay, it's going to create a little crack here, pull plates in opposite directions. But as it's going on the surface, it begins to cool, so that becomes more dense. Then it hits the core where it is heated again, and this whole process repeats. Now, obviously, there's more than one current, so where the currents come together, you might have a convergent boundary because, again, there's more than one occurring at a time. So this is what's driving the plate motion. So this is what Wegener did not know about. He did not know about the convection currents going on inside of the Earth to drive the plates. He, again, thought it was the waves and tides. Not correct. So he did not have the benefit of knowing about convection currents occurring in the mantle. All right, so again, here's another picture. Here we see divergent boundary. Here's a convergent boundary, and here's a transform boundary. All right, all you guys have left to do for today is a little practice, okay? So it's just the next page of your notes. It's just a little review of the notes and the article. Feel free to use your notes. Feel free to use the internet to help you answer some of these questions if you like. Down here, you're not going to be, well, you do have paper copies, so you can make these drawings. If you've lost your paper copy, you'll have to do that on a separate sheet of paper or something. But go ahead and answer these questions and make the drawings and label them. And I will be collecting this at the start of class tomorrow. Have a good day, and I will see you all tomorrow as we continue our discussion of the interior of the Earth.